going to connect my iPad real quick. Tyler, do something entertaining.
To be honest with you, I wasn't expecting this, so
Give me a second, I'm working. Oh, crap. All right, hold on. Sorry, Costin, I have to like go to our chat to find the thing because I don't have it saved. All right. Can everyone hear me well enough and see hopefully soon?
Yeah, you should be good.
Okay. Awesome. All right, so I'm just going to talk about the first unit pretty briefly. I guess if you have any, I'll stop like at the end, and if you have any questions, go. Or since there's only like 4 y'all, stop at any time if like something doesn't make sense. But one of the things I'm going to talk about real quick is just uncertainty. So there's always an uncertainty question on y'all's exams, and there's probably going to be one on the final. But essentially, the basic concept behind uncertainty is this equation that's like highlighted at the top, this like delta F of x. And all that means is that, oh, can I write on this? Maybe. Oh no, I might have to export it to Notability. Oh God. Okay. You know what? We're just we're gonna talk through this because it's gonna be too much work to move it. But essentially, like if you have an equation, you have f of x, and if it wants you to calculate uncertainty due to one variable, say I don't know, like r or something like that in Coulomb's law, you would do your equation, and then where you would just insert r, you would do r plus delta r. So exactly like what it says in this equation. And then subtract your original value, and that'll give you your uncertainty in like your overall function due to one variable. And like it says at the bottom, total uncertainty due to however many factors you want is just going to be this equation at the bottom, which you're just taking the magnitude. But okay, moving on from that. All right, Coulomb's law. Okay, actually, I think it probably would be better for me to be able to write. So let's see how well this wants to work. Where'd it go? There it is. Okay. All right. Cool. So here's Coulomb's law. Whenever you're doing problems in this class, always start with this version of it. And so I'm mainly just going to focus on the difference between like R magnitude and R vector. So let's say, for example, you have like 2 points here and you're asked to find like the E field at this point. I'm going to call it point A. And so if we're looking at this, I'm going to call this point B, we'll be generating some sort of E field somehow. The difference between R magnitude and R vector is that you have an X, oh, that's definitely Y, an X and a Y component to your R magnitude, and so, or your R vector. And so this hypotenuse essentially is always going to be this this R, and then the R with the hat on it is going to be your unit. So that's going to be depending on your X or your Y. So like if a problem asks you, hey, what's the X component of E field or the Y component, you would take kind of this section or the other section according to whatever it's asking. The reason why at the beginning of this unit, a lot of times we ended up working with R squared is because when you're working with something that's all in one direction, that R vector would cancel, which is how your R squared comes in the bottom. But I recommend just always starting with the R cubed because you'll always get to the right answer through that. Superposition, but this is pretty straightforward. You know, you just add up your vector components for whatever it wants. Also, if anyone has any questions, just say something. Not a huge deal. I'm just trying to go through as quickly as possible so that I don't go over for too long. All right, one of the bigger things that we cover in this unit has to do with charge distribution. So whether you're working in 1D, 2D, or 3D, you always have like this first component to DQ, which is lambda for 1D, sigma for 2D, and rho for 3D. So that always stands for charge density symbols depending on like what dimension you're working with. And then that DL always remains the same respective to whoever you're doing, you know, like DR or something like that. And your charge density, like it says right here, lambda in this case is linear charge density. So if I have like some charge object or something like that, just cut into all these pieces, charge density would tell me, okay, hey, this piece is worth this amount of charge. And in order to get total Q, you just integrate dq. This is familiar, you guys have seen this before, you know, it comes back in the third block, but just be mindful of whether you're working in 2D or 3D and like what that pertains to. So in 2D, you're going to have to be working with area, and then in 3D, it's going to be differential volume. I'm trying to think of any pointers. Yeah, I would say whenever I feel like a lot in 2D or 3D and like what that pertains to. So in 2D, you're going to have to be working with area, and then in 3D, it's going to be differential volume. I'm trying to think of any pointers. Yeah, I would say whenever I feel like a lot more times this 3D is more common in what we end up doing. And what I always end up doing if you can't remember something is just all you kind of really need to know for this unit as far as equations are volume of a sphere and volume of a cylinder. I would say those are like the main two. And so if you can't ever remember your dV, just take the derivative of volume. So volume of a cylinder is going to be pi r squared h. So dV would be 2 pi r h dr, right? Watch your units also, like I said, because you're working with, make sure they're like appropriate for the dimension that you're working in. But I think that's all I have for this unit. We already talked about this. Oh, so sorry, I forgot to mention this, but whenever we're working in, like I said, kind of stuff that has to do with charge distribution, there's uniform and non-uniform charge distribution. So if you have something non-uniform, it's pretty clear. They'll usually tell you like, hey, rho is equal to 4r cubed or something like that. But if they tell you that something is uniformly distributed, exactly like the slide says, that's total charge over total length for 1D, or if it was 2D, it would be total charge over total area or volume, right? And just make sure that, I think the easiest way to do this is to really just draw a picture of your situation. So if I have, I don't know, like some sphere and you're working at some radius where, or I guess it doesn't really matter for right now, but just ensure that you know kind of with your boundaries and what you're drawing. I think it's always easier to make sense of that, but that's how you would find a uniform charge distribution. Don't really want to work through any examples right now because we can come back to it later. But does anyone have any questions so far? Or can I just move on to Gauss's law briefly? I'm going to take that as no one has any questions. But, okay, real quick, this is Gauss's law. Y'all hopefully recognize this. But essentially, I think there's a slide about, yeah, okay. So the two things we're going to talk about really quick are the simplifications you can make for Gauss's law, just like Nick has on this slide. So if your E field is uniform and parallel, then you can essentially simplify to this equation down here. And dA always stands for, it's like the vector that's normal to your surface. So it's going to represent surface area. So keep that in mind. And then, oh, I'm ahead of the game. All right, actually, we're going to just talk about this really quick. But essentially, whenever you're working something with Gauss's law, I feel like there's always a lot of confusion as to what radius you want to use for something. So I'm just going to make up. All right, you have some sort of, I don't know, sphere, and you're working at this radius inside. Looks like a donut. But always, 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 the left-hand side of your Gauss's law always deals with your Gaussian surface, whether that's inside or outside, wherever, that's always the R that you're looking at. And then the right-hand side is where you have to be a little more careful because that Q enclosed deals with like your charge distribution and everything. So that's when you have a different radius or something like that. That's where you have to kind of be more careful when you're integrating rho dV in this case. But we can kind of go over that in a problem later if y'all want. That's just kind of big picture what we're working with Gauss's law. And Yeah, I think the rest of these are examples. Maybe. Yeah. Okay. So I think that's pretty much all I have for the first unit. Like I said, these are just kind of like really big reviews. If you guys have any more questions, feel free to ask like now at the end of each thing. And then at the end, we're also going to go over problems. So if you want, we can work through stuff from the first unit. But I think that's all I have for unit 1. All right. Tyler, are you doing unit 2?
I am, and I take it that nobody has any further questions about that. So I will go ahead and share my screen here. Thank you, Izzy.
Yeah.
Cool. Alrighty. Everybody can hear me / see this set of slides, right? Take it when it comes up in a second.
Yeah, I can see him.
Cool. Thanks, Izzy. All right, guys. So I'm going to talk about block 2, which is the circuits block. Probably the block that's easiest math-wise, but can be a little bit difficult conceptually. So really, we just got a few main concepts to hit over, and then I'll let Nick take over as far as magnetics are concerned. So first things first, whenever we're dealing with a circuit, any circuit of any kind, the driving force in a circuit is current, right? And current mathematically is the derivative of charge with respect to time. So how much charge moves through my wires over a certain amount of time, right? And remember, charge is the flow of electrons in our circuit, right? So mathematically, you might have to take the derivative of a charge function with respect to time. There's a couple of questions kind of like that sprinkled in the reviews, different places. So keep an eye out for that. And that is on your formula sheet, by the way. But nothing else really as far as straight up current is concerned. That's an example, right? Obviously, we can work backwards, right, and integrate our current with respect to time to find charge, right? So just remember the relationship between current and charge, right? The derivative of charge is current. The integral of current is charge, right? Working back and forth. So a lot of examples here, which we can go over if you guys have any questions. Next major topic we hit in circuits was the idea of resistance, right? So basically, how much effort does it take to shove a charge through a wire, right, or something equivalent, right? And we found a couple different formulas for resistance. This one here discusses resistivity, right? So when we're talking about a wire with a specified length and a cross-sectional area, and we're given some value for for rho, which is called the electrical resistivity. Right, in this sort of problem, we might be asked to find just the total resistance of some wire, right? And it would give you these dimensions pretty straightforward, right? It wouldn't do anything really confusing as far as that goes. So resistivity problems are fairly straightforward in the sense they will pretty much just tell you that, hey, rho is this, length is this, and area is this. Find the resistance of this amount of wire, things like that. I would say just remember that it does have a differential form, right? So if you're given find the resistance of this length of wire with a variable electrical resistivity or a variable length, things like that, you'll have to take an integral, right? But nothing too fancy, right? We don't make you do anything more than a U sub in this class, so nothing too complicated going on there. All right, more examples. All right, so now we hit kind of the major mathematics in circuits, right? So let's say we had a circuit that looked like this, right? A series circuit. We're going to call this our battery here, right? We're going to, whoops. Right, we're going to have a resistor here, right? A resistor here, all right, and a resistor here. All right, R1, R2, and R3. All right, so with this configuration, really, or any configuration where resistors follow one another in a line, we say that those resistors are in series, right? And whenever we have series resistors, to find the total resistance of our circuit, right, we just have to add them straight up, right? No fancy math going on here with series resistors, right? Just add them straight up to find our total resistance. On the other hand, right, parallel is a little bit easier to understand the configuration, what it necessarily looks like, but the math is a little bit, you know, kind of annoying. So let's say I had a configuration that looked like this, or something similar to that. We'll add R1, R2, and R3 there, right? Those resistors would be considered to be in parallel, right? Obviously, these are a parallel to each other just based on our definition of what parallel even means. But parallel resistors would see the same voltage, right? In the sense that this whole top wire here is at some voltage, right? The voltage of the battery, let's say, the battery, right? And this entire bottom wire here would be at a 0 voltage, right? So that's what we say things that are in parallel see the same voltage, right? They're between the same two nodes, right? And then the way we would add those up to find the total resistance of our circuit would be that 1/, relationship, right? It would be 1/R1 plus 1/R2 plus 1/R3, and we take the inverse of that sucker, right, to find our total resistance. I would just say to keep in mind that normally circuits aren't as easy as all series and all parallel, right? Just keep in mind that we can combine both of these rules, right? So if you had a really convoluted looking circuit, you might have to combine some things in series first and then do a parallel calculation, something like that, and then, you know, add more things up in series. It can differ based on the circuit you're given, but keep in mind that these rules do mix with each other, right? It's not, a circuit doesn't have to be entirely in series or entirely parallel, right? So just keep in mind that parallel calculation is that 1/, relationship, and series calculation is just that straight up addition, right? That's the main takeaway from series versus parallel resistors, right? All righty. Before I move on kind of past resistors and current, things like that, does anybody have any questions? Feel free to speak up or put something in the chat. I didn't hear anything, so nothing so far, but let's stop for just a second. Cool. I will take that as no. All right. So moving on to a little bit more of the equations we use in circuits. Hopefully you guys are familiar with this one right here. This is one we used a lot this semester. This is the equation for electrical potential energy, right? We use it a lot in circuits to find the potential energy of some object, right? So mathematically, that's the change in potential energy right there, right, is equal to charge times the voltage difference, right, between, normally we use it to find energy in a capacitor, right? But if you had a voltage difference between two objects or between two plates, things like that, this is where we would use this equation, right? Or mathematically Q delta V there, right? And internally related to the energy of a system, right, would be the power, right, which is the derivative of energy with respect to time, or energy would be the integral of power with respect to time, right? And then power, as you can see down here, has a few different equations, right? Most notably I delta V, right? But remember Ohm's law, V equals IR, right? We can substitute anything we want in this equation, right? Either I or V for our other variables and get different forms of that equation, right? So if you're asked for the power going through a resistor and you're not given the resistance, but you're given IV, well, there you go, you got that. Or let's say you're not given the current, but you have voltage and the resistance, right? You can plug that in into this form right here and find it that way, right? Just keep in mind that the formulas that are on your equation sheet sometimes aren't all encompassing, right? They're there because they're the easiest ones to list out, but remember they do have their own different components, right? Based on the variables that you're given. I do see somebody commented that they can't see what I'm presenting. I'm confused as to why that wouldn't be showing up because I can see it just fine. But yes, this will be recorded and posted somewhere for you guys to find. I believe Nick has posted them before on LongCap or sent out as a link, something like that, right? You'll be able to see this later. Don't worry about it. All right. So that's kind of it for power and energy there, right? Like I said, just keep in mind that those variables are internally related, right? So we can change them however we would like, right? Just keep that in mind. Another, I guess, big topic to hit in the circuits unit would be Kirchhoff's two laws, right? The current law and the voltage law, which we'll go over next. Right? The first of his laws, the current law, just says that the amount of basically whatever's coming into my junction has to come out. And what we mean by a junction, if I were to just draw a quick little circuit here, right, let's say I have this right here, some terrible resistors, right? Any place where two or more circuit elements meet would be called a junction. Right, so if I were to label them in purple, I could say, hey, that's a junction right there, and so is that, and technically this would be one down here, but this entirely would be one. So junction just means where two or more circuit elements meet, right? So that is saying that the amount of current entering my junction has to equal the amount of current leaving my junction. So let's say I have some value I1 right here entering my junction. I'm going to have an I2 right here, and an I3 right here, because my current will split at this junction right here. Right? So really this is just saying mathematically that I1 must equal I2 plus I3. Right? We can't lose energy anywhere. We can't lose any charges anywhere. They had to go somewhere, and in this case, they split between those two resistors. Right? So just keep in mind, we got to always conserve energy. And that's what Kirchhoff's current law is saying. On the other hand, Kirchhoff's voltage law says that if I draw any closed loop in any circuit, right, the sum of the voltages in that loop has to be equal to 0. Again, because I can't lose or gain energy anywhere. Right? So if I were to draw another circuit here, right? Let's draw something a little bigger. We'll do that there, and then we'll have basically the same thing. All right, so first things first, I kind of want to define, I guess, what a loop is, right? A loop would be, and the way I would define it, would be to any path you can draw in a circuit, right? So starting from one place and ending at that same place, right? So this circuit, for example, has 3 distinct loops, right? I could say this would be one loop, right? Starting, let's say I started here, right? I would go all the way around this first loop here, right? And end up in that same spot. That would be my loop 1. Right, I'll call that L1. Right? And then I could have one doing the same thing on the other side. Right? Let's say I would start here. I would go around the outside, and I would go straight back up. Right? That could be a second loop. And then the third and final loop would be really just around the entire thing. Right? We'll call this L3 just around the entire thing. Right? Because I could start at the battery, go all the way around the outside, and come back up. Right? So what Kirchhoff's voltage law is saying is that no matter which loop I choose here, the sum of the voltages in this loop has to be equal to 0. Right? So no matter what my sign convention is, no matter which way I decide to go, counterclockwise, clockwise, no matter what elements are even in my circuit, the sum of the voltages in that loop that I draw has to be equal to 0. Right? And if you're a little confused as to what we mean by the sum of the voltages, right, that would be really just looking at every circuit element, right, and figuring out whether it takes or gives voltage, right? So call it R1, R2, 3, 4, and R5. Right. In Phys 2, I believe the convention is whenever current encounters a resistor, we say that's a decrease in voltage, right? You can think of resistors kind of like parasites on our circuit, right? They take energy away from our reservoir, which we could call just our battery, right? We start out with some fixed amount of voltage. Let's just say we've got 2, 3, 4, 5 resistors. Let's say we got 10 volts in our circuit, right? And let's say, for example, when current first hits R1, let's say it takes, we'll say it takes 3 volts, right? So that means that there's 7 volts total for the rest of this circuit to take up, right? Or depending on which loop I choose, right? Just keep in mind that that energy cannot be lost anywhere, right? And no matter what loop I choose, no matter what circuit elements I have, energy has to be conserved, right? That looks like, so this is kind of what I was talking about, the sign convention, when it updates here in a little second. Nick is right. Yeah, the convention is 100% to go clockwise around a loop, right? But you don't have to, right? You can go any which direction you want. You just have to make sure you stick with your convention, right? If you establish clockwise as positive, then counterclockwise better be negative, right? Things like that. You just have to be consistent within your own notation in order to make sure you end up with the right signs on all your terms, right? An example of what that looks like, we can go over this if you would like. It's a very, very good problem. I believe it was a studio problem in Studio 2C, I believe, 2B, 2C, something like that. But we can definitely go through this as an example if you guys want to see that. Other than that, I'm kind of running out of time, so I'll really quickly talk about capacitors. Right, capacitors were those cylindrical-looking devices we worked with a little bit in circuits. Those of you that were in person, right, and they are basically like giant buckets, right? They store charge. Right, if we plug them into a circuit, we count them as empty to start, and then they slowly charge up and become more and more full over time, right? Just like a bucket with a hose would be, right? And I'd say the formula we used the most often was this relationship between capacitance, charge, and voltage, right? So as a definition, right, capacitance would be equal to the charge that the capacitor stores divided by the potential difference across those plates. Right? Keep in mind that capacitance also equals epsilon naught A over D, right? Where epsilon naught is the permittivity of free space, A is the area of your capacitor plates, and D is the separation between your two capacitor plates. And one more thing to keep in mind is that this formula deals with the physical dimensions of the capacitor, whereas this formula deals with kind of what's the properties of the capacitor, right? What it's storing, what the potential difference is, things like that, right? If I would be shocked if you got a question like this, but if it asked you if capacitance changes based on if Q or V changes, right, that would be no, right? Q and V will change with respect to each other, right? Whereas if I change the physical dimensions of my capacitor, say like my area of my plates, then my capacitance would actually change, right? You always got to remember that capacitors are physical objects, right? I can't have a zero capacitance if I make it not store any charge, right? Which is what you would get if you plugged in Q equals 0 to this formula right here, right? And hopefully you guys remember that from your second exam. That was a problem on your free response. But capacitance is not dependent on charge or voltage, right? Only dependent on these physical dimensions right over here. All right, so just keep that in mind. They're physical objects. They cannot have a capacitance of 0, right? Keep that in mind. And I guess, yeah, I'll breeze over that real quick. More formulas to deal with energy stored in a capacitor, right? 1/2 CV squared. And similar to the equation for power, just remember that we have multiple forms of this equation because we can rearrange C equals Q over V multiple times, right? So keep that in mind that while the equation in your equation sheet is 1/2 CV squared, right? You can absolutely get things like 1/2 Q squared over C, or there's one more that I can't remember off the top of my head. Right. Just remember that if you're not given a variable, then it shouldn't appear in any of your equations. So you're able to kind of rearrange that equation how you see fit, which is a very, very good thing. I believe, yes, one of the last things I'll talk about, capacitors in series and parallel versus resistors. Right. The main takeaway from capacitors versus resistors is that they basically act in opposite ways. So capacitors in series, right, something like this, right? If I were to find the total capacitance of this system, I have to add them up like resistors in parallel, right? So the 1 over relationship, right? 1 over C1 plus 1 over C2, right? Inverse that, that would give me my total capacitance for a series circuit, right? Again, different than resistors, right? Just keep in mind that those are not the same. We don't add those up the same way. Series capacitors are added up like resistors in parallel. And obviously on the other end of that spectrum, capacitors in parallel are added up like resistors in series, right? So if I had this configuration, apologize for the terrible picture, right? But if I had that configuration, then my total capacitance would just be the addition of all of those together, right? C1 plus C2 plus C3. Right? And those formulas are on your equation sheet. They're just in a way that's kind of weird to understand. They have the sigmas and things like that in them, right? Just keep in mind that resistors and capacitors act opposite each other, right? Capacitors in parallel add like resistors in series, and so on and so forth. Alrighty, so that's an example. Good example though. All right. Cool. I believe the last thing we'll talk about, and then I'll pass it off to Nick, just so we don't take too much of your time, is the concept of dielectrics. Right? And dielectrics are, by definition, some extraneous material that we put in between capacitor plates that ends up increasing the capacitance of our capacitor. Right? So sometimes it's like nylon, sometimes it's rubber, things like that. Just random, seemingly random materials. And the only effect they have on your capacitor, right, is by modifying what we call the permittivity of free space, that epsilon naught constant right there. And in every single one of these problems, you'll be given a dielectric constant, which looks like this, kappa, right? All the dielectric does to the capacitance is just multiply onto that permittivity of free space. It makes, it allows for a smaller electric field, which means a smaller voltage between those two capacitor plates, which will increase the capacitance of your capacitor, right? But mathematically, all it is just multiplying kappa onto epsilon naught, right? So your new capacitance is just kappa times your old capacitance, right? Keep that in mind for a mathematical type question. Yep, very, very good pictures here. All righty. I think that's about all I had for circuits. Yeah, good unit, but pretty lax mathematically. So in that case, looks like we'll pass it off to Nick, but does anybody have any questions about the circuits unit before I do? Right, if you can't think of any right now, just ask later, but no big deal. I'll leave a couple seconds for you guys to ask. Cool. All right, Nick, looks like the floor is yours.
Awesome. Can everyone hear me okay?
I can hear you just fine, bud.
Awesome. And unfortunately, my computer decided not to turn on, so I'm doing this off my phone, but I think I can still do everything.
You should be all right.
Cosmic, if you want, we can like wait if you need to get your computer or something like that. We can always do some practice problems and then come back.
That's fine. I think I have share on my phone. I just have to figure out how to get it to work. Can people see my screen?
Yeah.
Okay, awesome. So now if I go to my, let's see, downloads. Whoops, that's embarrassing.
If you want, never mind.
Is like the big bubble with IG right now in the way?
Yeah.
And I'm sharing. Okay. I don't know if there's much we can do about that, but I think this is fine. Okay, I'm just going to do a quick run. Block 3. And block 3 started with the Biot-Savart law. The Biot-Savart law is, of course, the sort of magnetics equivalent of Coulomb's law, where we have some arbitrary current, and we can define a differential length vector that runs along that current, and then also an R vector that points from the source, which is in this case the current, to the observation point. If we put all those together, that can give us a dB as per the Biot-Savart law, and this gives us a recipe for finding magnetic fields from current carrying wires. So for instance, if we had this red current carrying wire here, the DLs would point along the red loop, and then wherever we want to observe the magnetic field, the R vector would point from the source, from the source to the observation point, kind of like that. And we can work through that problem later if needed. Still going. Okay. The next big topic in Ampere's law, in block 3 was Ampere's law. And Ampere's law, as it reads on the equation sheet, is the closed loop integral of B dot dl equals mu naught times I through. And then in block 4, we also learned about the displacement current term, but for block 3, that doesn't matter. So the left-hand side is just a closed line integral. That's the closed loop integral that we take over the Amperian loop. And the right-hand side of Ampere's law is whatever the current enclosed is. So for instance, if we have a current carrying wire that's carrying current out of the page, it creates sort of a loopy field that's consistent with the right-hand rule, where our thumb is the current and the other 4 fingers are the B field. Okay. Let's see, that's just more on Ampere's law, which I think is best understood through problems, so we can work through that later. Okay, magnetic flux. This is sort of just an intermittent topic that came up in block 3. Magnetic flux is obviously very similar to electric flux. It's the same principle, except with a magnetic field instead of an electric field. It's the integral of B dot dA. So, yeah, sometimes we have to, when we got to the end of block 3 and we were doing Faraday's law, the right-hand side of Faraday's law is obviously the time derivative of magnetic flux, but sometimes we had to take the integrals there, sometimes we didn't. Just know that this integral definition of flux works in all cases. And if the surface is completely closed, then the magnetic flux going through that closed surface is going to be 0. This is one of the 4 Gauss's law equations. But again, it's not terribly useful. Okay. Now moving on to topic 3C, which is magnetic forces. So magnetic forces tell us that the force that is exerted on a particle of charge q moving with velocity v in a magnetic field is qv cross b. So this is where the right-hand rule came into play very strongly. So our governing equation with all magnetic force problems is F equals QV cross B. So the way we can apply that with our right-hand rule is to set our index finger to be the V term, our middle finger to be the magnetic field, and then our thumb is the force. So for instance, if I have a B field pointing into the page here, that's what the little circle with the X through it means. Then if the particle is going to the right, the force will necessarily be pointing upwards. And in fact, if a particle is moving completely perpendicular to a magnetic field, then that force is going to be a centripetal force. Because if we go back to this picture, with our index finger pointing to the right, our middle finger pointing into the page, our thumb is then pointing up. So if we imagine sort of right here, as the particle enters a magnetic field from the left, moving to the right, we have a force that's going to push it upwards. And that force sort of steers it a little bit up and then up some more. And that force is a centripetal force. So it's going to move the particle in a circle. That was the case if the velocity was completely perpendicular to the magnetic field. But if the velocity had some component that was parallel to the magnetic field, then it's no longer the case that the particle moves in a circle. Now the particle is going to move in a helix. So we still have the tangential component of the velocity. That doesn't change. Because the velocity, we can express the velocity essentially as the sum of its parallel component and the component that's parallel to the, we can express the velocity as a component that's parallel to the B field and a component that's perpendicular to the B field. The component that's perpendicular to the B field is still going to behave the same way as before. It's still going to move it in a circle. But the component that's parallel to the B field, all that's going to do is sort of, instead of keeping the particle in a circle, it's going to push it upwards in a helix shape. Because, again, the governing equation is F equals QV cross B. So if it's a parallel component to the velocity, that won't interact with the cross product, and hence that component of the velocity never changes. Awesome. And one consequence of magnetic force equation is that magnetic fields never do any work because work is defined as the integral of F dot dl, but the F vector is always perpendicular to the dl vector, just sort of by consequence of the cross product and how the dl is parallel to the velocity of the particle. Let's see here. And then the other force equation that we encountered a little bit in block 3 was the force on a current carrying wire. We have that dF, the differential amount of force, is equal to I dl cross B, where dl is just an infinitesimal segment of that wire. Let's see, this was the free response on the last exam. And then we got into torque, which is topic 3D, I think. So torque, we know from Phys 1 is R cross F, or if we want to look at differential torque, that's R cross dF. The R vector is not the same as the R vector we know from Coulomb's law or from the Biot-Savart law. This R vector is the one that points from the axis of rotation to the point of force application. The R vector that appears in Coulomb's law and the Biot-Savart law points from the source, so either from charges or from current carrying wires, to the observation point. So just keep that distinction in mind. And this is pretty similar to the block 3 free response. And if it's a current carrying loop, and if it's a closed current carrying loop, then we can define the magnetic dipole as mu equals Ni times the area vector, where the area vector is normal to the loop that defines it. And then the torque is just that magnetic dipole mu cross B. All of this is on the equation sheet. Okay, motional EMF. So sometimes the motion of charges through a magnetic field can induce an EMF. So for instance, if you have a conducting bar that's moving with a velocity v in the presence of a magnetic field, by virtue of that conducting bar containing charges, those charges are going to be subject to a force, the same force we know from QV cross B. So for instance, if we think about the positive charges in that rod, if the B field's pointing down and the velocity is sort of coming out of the page, then the magnetic force is going to push the positive charges to one end of the rod, leaving residual negative charges at the other end. And what happens is that sets up an electric field. Electric fields always point from positive charges to negative charges. So that electric field is in the opposite direction of the magnetic force. And what we have is that the electric force and the magnetic force cancel, and we get the expression E equals VB, which comes up again and again. We can integrate that expression to find the voltage across the rod. How am I doing on time? And are there any questions? Okay. Let's see, right here. There's a motional EMF problem that we can look at later if needed. All right, Faraday's law. This is sort of the last big topic from block 3. So Faraday's law, it's expressed in this big integral form, which is pretty scary. But fortunately, we don't really have to deal with this integral form. The right-hand side, as I mentioned earlier, is just the time derivative of a magnetic flux through some surface. The surface could be any open surface. So for instance, if we have a loop of wires, that would be the magnetic flux through the circular loop. And then the left-hand side of Faraday's law is a closed line integral, but what it boils down to is that that closed line integral is just the EMF on that same closed loop that defined the area in the right-hand side of Faraday's law. That gives us a pretty concise way of expressing Faraday's law as the EMF is equal to the negative time derivative of the flux. Whenever we have magnetic flux through an open surface changing for any reason, there will be an induced EMF. And Lenz's law tells us that when a thing, a current, an EMF, or a B field is being induced by Faraday's law, what's being induced will act in such a way to oppose the change that caused it. So that is explaining the negative sign in Faraday's law. That sort of just tells us maybe if I have a B field that's increasing out of the page, then the induced current will set up its own B field that's pointing in the opposite direction. And I think that's it for block 3. Let me stop presenting. Any questions there?
Cool. Well, thanks, Nick. I appreciate it. It looks like Kate, for whatever reason, cannot get into this meeting. So I can do a short little thing on block 4. It's not a huge deal because there's not too much information to cover and it's pretty fresh in people's minds. So I'll take care of that. All right. I guess while we're finishing up here, guys, please make sure to vote on which problems you guys would like to see. Each of us have got a few example problems kind of in mind necessarily, but there's always exceptions to that. So please go vote on which problems you would like to see, and we'll go through those as soon as I finish up here. So cool. So we don't have any slides prepared for this, but hopefully optics is fresh enough in your mind. We really just got a few major points to hit home. So topic 4A, right, was just about the nature of electromagnetic waves, right? Talking about some of the basic equations we could use, some of the basic quantities, things like that. Right, so everything we remember from phase 1, right? Things like wavelength, frequency, velocity, all that good stuff, that still applies. And there's multiple equations on your equation sheet that describe how we can relate those variables to each other, right? Just in terms of wave properties. All right. And then important thing to remember about electromagnetic waves is that they do have momentum, right? So they exert forces, right? And then on your equation sheet, you'll have a couple different equations that deal with this. Right, they're the intensity equations, right? So I use the variable I, but on your equation sheet it has S for the pointing vector. I think that's very aptly named, right? But intensity, right, is going to be power, right? Usually the power carried by your electromagnetic wave divided by the area over which it extends, right? The most important thing to remember about this equation is that this area term refers to the surface area of a sphere, right? And the reason why that is, if we had, let's say we had a radio antenna here, right? And I wanted to feel, or I wanted to figure out what the intensity of the light was over here, right? If we were to draw this pictorially, we would say that our waves move in a spherical fashion, spherical shape, away from whatever is making them, right? So if I said the top of this radio antenna was making our waves, right, they would go out spherically from there until they hit wherever I was at, right? And they're all spheres. I just didn't draw the rest of them because that would interfere with my my other writing. So, right, we said that that area is a surface area of a sphere. Right, keep that in mind. That's, I would say, probably the most important part about that intensity formula, right? And then sometimes be on the lookout. It might say hemispherical or semispherical, things like that. And in that case, you would have to either divide it by 2 or divide it by 4, things like that. All right, so just keep in mind your spherical geometry there. All righty. That pretty much takes care of 4A and 4B, right? Some of that physical, or some of the stuff about optics and waves, things like that. 4C was all about geometric optics, right? I'm sure most of you either loved that or hated it, right? Dealing with triangles and the usage of Snell's law, right? Snell's law says that the index of refraction of the material that the light is first in times the sine of the angle to the normal that it comes into our prism at is equal to the same formula, but dealing with everything on the inside of a shape. So let's say that I have a triangular prism here. Right, and I've got light coming in at, let's say, that angle right there. Right. First things first, it's important to realize that the angle it's referring to is the angle to the normal, right, to the normal of that face. So that would be my θ1 right there, right, the angle at which that light wave is incident on my shape. Right, and then it would say, usually this is air out here, but sometimes it's water, things like that. So it will give you a corresponding index of refraction. For air, it is 1. I can't remember off the top of my head what water is. I want to say it's 1.3 or 1.5, but it'll tell you. All right, and then what it does inside this prism is what we call refraction. Right, the light wave bends. Right, and in this case, I'm just going to draw it straight across. You guys might remember this problem. Right, but this would be prism is N2. Right, and then that angle theta is still to the normal, right? That would be my θ2 there, right? So let's say if I wanted to find, say, the index of refraction of my second shape, or my shape in the first place, right? I would know all of these other variables. I would know N1 sine θ1 and sine θ2, and I could rearrange that to solve for the index of refraction of my sphere, or my object, sorry. All right, and then it will do the same thing as it leaves this light wave, something, or as it leaves this prism, something like that. Right, so Snell's law is very, very repeatable, and honestly pretty easy to calculate, even with those terrible calculators. Right, just remember that it deals with light refracting, not reflecting. Right, if we're dealing with reflective light, it always reflects back at the same angle that it entered the prism. Right, keep that in mind because there might be some trickery wording, some things like that. All righty, that's pretty much it for geometric optics. Really, the last area we covered was 4D, and that was physical optics. All right, how we use them in physical situations and things like the double slit experiment. All right, and the main takeaways from this studio and this topic was really what came out of 2 different formulas, one for constructive interference and one for destructive interference. Constructive interference referring to when 2 waves are in sync with each other, so their highs or their peaks add up, right, and their valleys also add up, right? So you get a massive wave, right, if compared to kind of a smaller one, right? So waves will add up. Right, and on the other end of the spectrum, we have destructive interference, where waves are out of sync with each other, and the peaks will cancel the valleys, so you just end up with nothing, right? So they will sort of, I guess, subtract from each other, I guess is the right way to put it. Right, but really they, in terms of, I guess, wording, I guess they cancel out each other, right? Things like that. So the constructive interference equation, right, is going to be delta R, right? The distance between those 2, whoops, actually, I'm just not going to say that. I'm going to say m lambda. M was the wave number of our wave. Lambda is the wavelength of said wave. Right, is equal to m plus 1, or I guess we'll just say M. Say M times, oops, sorry, this was supposed to be delta R, is equal to M lambda, right? Meaning that the path length difference between those two waves is equal to M, the wave number. For constructive interference is always whole number integers, 1, 2, 3, so on and so forth. All right, and times the wavelength of that wave, right, which will either always be given to you or you can find it using frequency, velocity, things like that. All right, and now destructive interference, same type of equation, except now we have half integers of our wave number, right? Destructive interference happens on every half, right? So it'll happen on 1 half, 3 halves, 5 halves, so on and so forth, things like that. Right, so it's important whenever a problem will say these waves constructively interfere or there is constructive interference at some location that you know which one of those two formulas to use because they're very, very similar. Right, just keep in mind that constructive interference is always whole number integers and destructive interference is always half number integers. All right, so I think according to my notes, that was all you guys learned as far as optics are concerned this semester, and I don't think I missed anything. Yeah, I think we should be good to go there. Right. I guess the last thing I'll say is that a lot of the equations for the optics unit are fairly self-explanatory and ways that they will lead you. So problems may ask you for intensity first, right? You'll find that, and then there's an equation later down the line that involves intensity and electric field, right? That is going to be, sorry, I can't remember it off the top of my head. It's equal to 1/2 times c the speed of light, epsilon naught, times the electric field squared. Right. So whenever problems ask you about, hey, what's the electric field generated at this point, or what better yet, what would be the voltage generated in this radio tower, right? The key to those voltage problems would be to solve for electric field first, and then use that integral we learned in Unit 2, right, to find the voltage based on that. Right, another pretty common relationship we use in the optics unit. All righty. So that was just a little hint there at the end. But all right, cool. At this point, I don't have anything else to say about optics. I don't know if Kate did. He's not here. At this point, if you guys haven't voted on that that other poll for problems, please do. Or, I mean, if you have, just feel free to let us know. We've got about an hour left. What problems would you guys like to see done? Keep in mind that they're all multiple choice, right? So they're not going to take you, like I said, more than 3 to 5 minutes usually, right? And they won't be anything super involved, like the free response question. So yeah, we're here for you guys. Just let us know what problems you would like to see, and we'll get those hammered out for you. Block 3, okay. Block 3, I'm not surprised. All right, anybody else?
It looks like the poll has kind of like pretty equal for all of them except for block 4, but it only has like one vote, so.
Well, block 4, the one I'm seeing, has 2 votes, so it's actually the most. Or is that what you said?
Yeah, I said it has 1 more vote than the other one, so.
I think you said it had 1 less. That's my bad. Cool. Okay. So in that case, looks like everybody wants pretty even distribution. I mean, do you want to just, Izzy, well, can we start with you and then we'll just go on and hit all these major points?
Yeah. So I'll start.
Looks like an uncertainty problem is definitely on that list.
Yeah, I can work uncertainty into the problem I'm doing. So I'm just going to pick a generic kind of Gauss's law problem. The one that I'm looking at right now, if y'all want to follow it, it's from topic 1D Studio, and it's just non-uniformly charged cylinder. So let me take over screen sharing.
Really quick, before I mute myself, if you guys, the block 3 and block 2, those are very, very helpful. Just keep in mind that obviously there's a lot in those units, so feel free to tell us what you would like to see most out of those blocks. Sorry, that's the only poll I didn't create. So yeah, just let us know what topics you're struggling with most, and we'll try to hit on those types of problems. Right. Other than that, Izzy, sorry, the floor is yours.
No, you're good. Okay. So like I said, I'm just doing a non-uniformly charged cylinder problem. I'm gonna write down some stuff from the problem just in case you don't have it pulled up. But essentially, y'all can see my screen, right?
Yeah,
Hopefully.
you're good. I can see it. I can hear you.
Okay. Awesome. All right. So I'm going to run through this problem one way, and then I'm going to talk about it the other way, because I feel like there's really only kind of two types of problems when it comes to stuff to do with Gauss's law, and that's whether you're looking like inside or outside this charged object. So the way that this problem is written is right now is that you are looking inside. So I'm going to call this radius R, and then let's say our Gaussian surface is this one, and I'm going to call this radius little r. So pretty much all you're told is you have a non-uniformly charged cylinder. What's your E field? So we're going to start off with Gauss's law, right? And totally up to what you want to do. I usually just start with Q enclosed, but since we're working in 3D, that means, well, any Gauss's law problem, or let me back up, any charge problem where you're looking at something like this, you're going to want to start with that general formula where it's like charge density times differential like length or area or whatever. Since we're working in 3D, and your given rho, you know that should probably be your charge density, and what goes along with rho is volume, so we're going to use differential volume. And if you were told that this was a uniformly charged cylinder, the only thing that would change in this problem is that you wouldn't be given this rho term, so you'd have to come up with it yourself. So the way that you would just do that is take your total charge and divide it by your total volume, and then you'd get your rho. But since we are given one, we can work with that. So you're told that your rho is CR squared, and then you need your dV term. So the way that I always do this, because I don't like memorizing a whole bunch of stuff, is I just derive the differential volume. So volume of a cylinder is going to be pi r squared times h. So dV is just 2 pi RH times dr, because you're differentiating with respect to radius. So that's what I'm going to put right here. And then I think the trickiest parts of these problems is determining what your bound should be. So obviously the lower bound is going to be 0. But as far as your upper bound, kind of determining which R you want to look at and why. And so this is kind of what I was talking about earlier, but I think the easiest thing to do with these types of problems is just honestly draw a picture. So if I were to say that the upper bound for this integral were big R, then what that represents is that the charge that you're looking at, or like the radius you're looking at, is this entire thing. So you're enclosing the entire charge. But that's not necessarily true, because what we're doing is we're looking at like a portion of that charge that's enclosed in our Gaussian surface here. So that means that our upper bound is going to be little r. So you're only taking like a portion of the total charge enclosed in this cylinder because you're at a smaller radii. Okay, moving on. All right, I'm just going to pull all the other stuff out of the integral. And then you're just going to have to integrate r cubed. Cool. So let me back up real quick. This is going to be your expression for Q enclosed. So we have that right-hand side of the equation taken care of. So when we're looking at the left-hand side of Gauss's law, the E dot dA, like I said before, there's kind of two arguments that you want to work for or look for. So if your E field is uniform, which you're told in this case it is, and if you have a and if your dA and your E field vectors are always parallel. So for example, let's look like right here, your dA vector is always perpendicular to your surface, and your E field is being generated radially outward. So the angle between those is 0, cosine of 0 is 1. So therefore that dot product goes away. So your left-hand side of your equation just becomes E times A. But like I said before, that A is for surface area. And so conveniently is the derivative of volume. That's how I always check. I think it's a good check that those should match up for you. But once again, the left-hand side of Gauss's law always deals with your Gaussian surface. So it doesn't really matter. You're always going to use like whatever R you're looking at. In this case, I denoted it as little r. And then we're going to plug in RQ enclosed over epsilon naught for the right-hand side of this equation. So this becomes this. Right? Yeah. Cool. Okay. Then we can start canceling stuff out. So this is why the length of whatever object you're looking at never really matters because it always cancels. Sorry, my screen keeps moving around also. But then you're going to get this expression. And that's going to be your E field for a point within the radius of the bigger cylinder. So does anyone have any questions on that? Okay. It doesn't look like it. Real quick, what I'm going to run through is, let's say that we had, rather than having like a little cylinder inside, let's say, okay, we're looking at some point like all the way out here. Oh, that's a really bad bottom. All right, so the only thing that would have changed at this point in time would be your Q enclosed term, right? Because like I said before, your left-hand side of Gauss's law is always dealing with your Gaussian surface. So this surface area would be, all right, I'm going to denote this as little r again. It would stay 2 pi RH, right? But when we're dealing with the right-hand side of Gauss's law, or the Q enclosed term, and you're dealing with your bounds, if I were to write 0 to little r here, what you're saying then is that the charge that's enclosed in our cylinder, the purple one, is actually enclosed all the way here, which isn't necessarily true, right? Because that'd be more charge than you actually have. So the maximum, like the charge extends all the way through the cylinder that you're looking at, but it can only go to right here. So your upper bound for that Q enclosed term would only actually be your upper bound R. And then you go around problem the exact same way. The only thing is that your R's are now going to be different, the left and right, so they wouldn't cancel. But big picture wise, that's kind of how you want to approach a Gauss's law problem. Does anyone have any questions on that? Okay, I'm gonna take that as a no. Oh, wait, actually, I could probably talk about uncertainty really quick if no one has any questions.
Usually the uncertainty problem deals with the potential function. So V equals, what is it, KQ over R. Usually it's that one for block one.
I mean, I'm just gonna use this E field one. It doesn't super matter.
No.
But yeah, okay. So anytime you have an uncertainty problem, all they're asking you to do, okay, actually the first thing you want to do is just write down this equation. This is like always what we use for uncertainty in this class. And all it means is, okay, let's say I have a problem that says they want to know the uncertainty in my E field equation due to R. So all you're going to do is you're going to take your E field expression that I have up here, and then you're going to plug in for this first part of the equation. So this right here is what we're doing right now. All you're going to do is anytime, if it wants uncertainty due to R, then every time you see an R, you're going to plug in R plus your uncertainty to your original equation. And then the second part of this equation just says, okay, hey, subtract the original version. So then you're just going to go, whoa, sorry. You're just going to go back and subtract. This will be that, and then this will be your uncertainty in E due to R. And the only thing that would change if you had, like, I don't know, let's say there was like I don't know, like a X associated in this equation, like another variable. And if the problem were to ask you for like total uncertainty due to both of these, you would do the exact same thing again. You would find your delta E due to X. So same thing, you would plug in uncertainty in X, subtract your original, and then your total uncertainty in would be like the magnitude of them. So you would take the square root delta E R squared. What's that squared? It's a really bad square root. And this will give you total uncertainty. And that's pretty much all there is to do with uncertainty. Yeah, I can't think of anything else with that. But does anyone else have any questions, or are we all good on block one? I'm gonna take that as a no. All right, Tyler, then you want to do unit 2?
I would love to. Yes, so you can definitely share your screen when we get to block 3. But first, I'm going to cover something in block 2, and then the floor will be yours. Right? No big deal. I'll let you know. All right. So Daniela, I read that your question was about a Kirchhoff loop question. Very, very good question, because they can be kind of confusing. But I feel like once you establish your convention and kind of understand how those things work together, you'll be just fine. So I'll go back to this one that I had on my slides. So see when that shows up there. Momentarily. There we go. Cool. All right. I assume everybody else can see it because I can see it on my laptop. So, all right. So this one we worked through a couple of times, right, in studio, and I believe it was a homework problem, something like that. But very, very good because you put it plainly, Danielle, there's a lot of stuff going on, right? A lot of voltage sources, other things. So the first thing I do whenever I'm presented with a Kirchhoff loop problem, right, is the first thing is just to draw my loops, right, to figure out how many loops I have and then figure out what directions those are going in, right? So I'm going to label the first one here in red. Let me get my thickness of my pen up a little bit up. All right, we'll call that loop 1, right? It's this bottom loop, right? So if I were to highlight it, right, it would be this bad boy right here, right? Starting from this point and going in a clockwise direction, right? That would be my loop 1, right? The second place I would go would be to this upper square, right? I'm calling it loop 2, right? I could start and end at the same spot, doesn't really matter, right? That would be my second loop, right? And then my final loop, right, has got to be the loop around the entire edge of the thing, right? So I'll start in the same spot, go all the way around, right? And that would be my loop 3. Right? Me personally, I like to always have clockwise be positive, right? So anything opposing my clockwise direction is going to be negative by default, and then my resistors that are taking that or any power away from my my system, those are going to be negative as well, right? So that being said, I'm going to start with my loop 1 here, right? And I'm gonna erase, actually, kind of run out of room a little bit on this thing. Yeah, I'm going to erase those loops because we've covered those. All right, I'll just say that L3 is there around the outside still. All right. But I will work over here on the right-hand side. All right, and we will start with loop 1 here. Oops, on red. So loop 1 is that red loop there. So it goes through these 4 elements, right? My voltage source 1, my voltage source 2, I3, 4, or whoops, I could just say R4 and R3. So I have those 4 elements to worry about. I can start with whichever one I want, right? I just have to end at that very, very same spot. So for simplicity's sake, I'm going to choose to start right here, right? So that way I go through my voltage source first, okay? So remember what we said earlier, right? If I enter a voltage source from a positive and come out of the negative, in Phys 2 we say that's losing voltage, right? Every time that happens, we say that is losing voltage. So what I'm going to do here first is start my loop equation by saying, oh, well, negative V1, or sorry, negative V2, sorry. That's a voltage 2. All right, because I go through that battery from the positive to the negative. So really, I started at, say, let's say randomly 10 volts, and I ended up at 0. That means I lost 10 volts, right? Just adding a number to that battery, right? So V2 would be negative, right? And then moving on from there, right? Once I hit I3R4, right? So this is going to be a little bit of a point of confusion for some people, right? And let me just make sure this is the problem I'm thinking of. Yeah, cool. I'm going to, despite the fact that this is going in the direction of my loop, right? It is a resistor, right? So it's going to be sapping voltage from my circuit. It's going to be taking it away from all the other elements in my circuit. So I'm going to subtract off the voltage that would be coming from that resistor, right? So minus I3 R4, right? Notice how that is Ohm's law, right? That is a voltage right there, right? So it doesn't always have to be adding up straight voltage values, right? It could be adding up I3 or I currents and resistors multiplied together, right? Because that is the same thing as a voltage, right? So got that one all taken care of, right? So if I go around my loop here, right, I've got these 2 elements already taken care of. So the third one, right, is R3 right here. Right, so I got to figure out what happens at this resistor. Notice that I2 is going through that resistor, right? So that's I2 right there. So normally, like I said, my convention was, okay, well, my resistors are going to be taking power away from my circuit, right? That's the convention I already established with R4 here, right? But notice how that current is opposing my original direction, right? So I have basically a double negative, which turns into a positive, right? So I2 R3, I believe it is. Yeah, I2 R3. Does that make sense? That's, in my opinion, the most difficult part about this circuit element, right? Is that my resistor is correct. I am taking power away from the circuit, but because that current I2 is opposing the direction of my loop, right? That's another negative. So really, I just end up with a positive term over here, right? And then the last thing I have to worry about is this voltage source right here, right? And similar to voltage 2, I enter it from the positive side right there and leave through the negative side, meaning that I lost voltage there, right? Meaning I would have to subtract off V1, and that would be equal to 0 by Kirchhoff's voltage loop or voltage law, right? So that's my loop 1. Right? That would be a valid loop equation for loop 1 there, right? Important thing to remember about these equations, it does, like I said, it doesn't matter which way you have your convention. Let's say if I said counterclockwise was positive, right, I would just get the negative version of this equation right there, right, as soon as that pops up, right? And the negative value of that is just as valid, right? It just might not be an answer because that wasn't the convention that was selected, right? But keep in mind, if you're doing these problems, you might get the negative equation of an answer, right? Just keep that in mind. It just depends on the convention that you choose. All right, so that takes care of loop 1, right? But remember, we still have 2 loops to go, right? So I'm going to start, we'll go into L2, and I'll pick up the pace a little bit this time because hopefully we kind of establish some conventions. So I will start up here in L2, meaning that the first element I hit is that V1 there, that battery, right? Different than before, I'm now going from the negative end of the battery to the positive end, meaning I've gained voltage in this case. Right, so I would be a positive V1 there, right? Carrying on from before, I would hit this R3 next, right, resistor 3, and I would end up with the same thing I had before with R4. I'm going to subtract off I2 R3 from this, right, because that is the voltage being taken up by R3, right? Current times resistance, right? Using Ohm's law, that would be the voltage taken up by R3. All right. Next in my loop here is I1 R2. Notice how I1 comes all the way down here, right? So remember, my resistor normally takes voltage away from my circuit, which it still does, but the current is going in the opposite direction of my loop direction. So it's going counterclockwise as opposed to clockwise. So again, that cancels out that negative, and I end up with a positive I1 R2. All right. And then the exact same thing with R1 there, right? Again, opposing the direction of my loop, but also it is a resistor, so it will take power away. So again, it's a positive I1 R1. And that is all equal to 0 by Kirchhoff's voltage law. All right, the last one we have to worry about is the big outer loop, right? So I'll erase everything in red and blue so we can see everything. So the outer loop is concerned with only the things on the outer edge of the circuit, right? So R1, V2, R4, and R2, right? I can start any point I want. So I'm going to say we'll start up here in the top right-hand corner again. Sorry about that. Some really annoying people next door. All right, so in my final loop, right, I'm going to start here. That means the first element I'm going to hit is that battery 2, right? That second voltage source, right? Similar to our first loop equation, I go from the positive end of the battery to the negative end, meaning that voltage 2 is going to be negative, right? Negative V2, right? And then exactly similar to the first loop, right? I3, R4 going to have to be negative because that is taking voltage away from my system. All right. And then these last 2 elements, right? R1 and R2, we just covered. We said that, okay, well, my loop direction that I established was positive was clockwise, but I1 is opposing that direction, right? It's going counterclockwise, right? So again, we get that double negative cancellation there. So I end up with 2 terms added together, right? I1 R2 and I1 R1, and both of those add on to that equation to equal 0. Right, so these would be my 3 loop equations for this particular circuit. Right, again, if I would have chosen my my convention to be counterclockwise was positive, I would get the exact same equations, but all their signs would be flipped. Right, and that is, once again, that is totally valid. Right, just keep in mind that people's conventions might be different than your own. Right, so again, if that answer key has a negative version of your equation, that would also be correct. Right, it just depends on which convention that you chose. So at this point, this problem is pretty much taken care of. Daniela, does this answer your question about the Kirchhoff loop equations? Is that clear?
Yeah, I got it. No, thanks.
Yeah, no problem at all. All right, in that case, I will stop screen sharing, and Sol, you go right ahead. Nick, you still there? Are you able to even answer questions?
I'm still here.
Okay, cool. All right, well, I will let you go right ahead. Sol, go ahead and share whatever problem you're talking about. We'll do our best to get on the same page, okay?
Okay. This is the problem from exam 3 that I got completely wrong. Can you see the screen?
I can see it.
Okay, cool.
Nick, do you want to like talk through this? Have Tyler draw it out, or what do you want to do?
I can give it my best shot. I can't write things obviously on my phone, but I can just sort of talk through it, and I think that would work for this problem.
I've got the problem pulled up on in my notebook, so you go ahead and talk, and I'll do my best to write over what you're talking about.
Sure thing.
Should I stop sharing my screen to share your screen?
You're good. I forgot I can take it from you. You're good.
Okay.
Alrighty, so I will go ahead, Nick. Sorry, I'm just gonna draw the thing.
Yeah, no worries. I'll just start talking about the problem then. Yeah, so that one, it was, let's see, we had a magnetic field that was pointing into a loop, and on the left we had a function of that magnetic field, sort of how it was changing with time. And as we previously asserted, whenever we have a loop and the magnetic flux through that loop is changing, Faraday's law asserts that there will be an induced EMF. So what was happening in that particular problem is that the loop was pointing. Yeah. If we start down by writing Faraday's law, so it was a great idea to start by writing the first steps. The induced EMF is equal to the negative time derivative of the flux. So I guess a great first start would be to determine what the flux is. And the flux is the integral of B dot dA. The B field was constant and uniform through that loop. It wasn't completely parallel to that loop. It wasn't parallel to the area vector of that loop. I think it was offset by 60 degrees. Yeah. But within that loop, it was uniform. So we don't actually have to take an integral. We can just multiply B times A and then include the factor of cosine of 60. Sorry, cosine of 30. Cosine of 30 because the area vector points normal to the loop. So the area vector is pointing straight up. So really the angle between the B field and the area of the loop is 30, not 60. Awesome. Cool, so that's the flux. And then to take the time derivative of that flux, the area is constant. It's just pi r squared. Cosine of 30 is obviously constant. The only thing that changes is the B field, which we can sort of just take the derivative of that by itself. And taking the derivative of the B field just amounts to finding the slope of that line from 0 to 2 seconds or whatever the time was. How's that all sound? And then I can't remember if that problem had a number of turns of the loop, but if there were like more than one loops to that coil, then we would also multiply by n.
Okay, it said it had 5 turns.
Yeah, so we multiply by 5 because there's five turns, so essentially that's happening 5 times.
You can think of n as just a multiplier on our area, right? Technically we have 5 circles, right? So we got 5 times the area, right? If that helps.
Uh-huh.
It actually worked pretty well, Nick. Does that make
Tyler,
sense?
great
Saul?
coordination. Great coordination.
Does that answer your question?
So the question was, what is the magnitude of the induced EMF? And so what would the slope be?
The slope would
Because
just be the slope of
I
that
could
line on
see,
the
I guess. Okay, I guess I could see that the rise is 0.3.
Yeah. So
Times 2. So,
that
divided by
question
2.
My apologies. I believe this question says it asks for the induced EMF over a certain amount of time, right? So you
yes.
have, like, this will be from 0 to 2 seconds right here, and I think it's like 2 to 4, I think is right there.
Yes.
So if it asks you
Yes.
for the EMF over a certain amount of time, you'll just take the slope of this B field function, right, during
Yes.
that time period.
Okay, so it would be 0.3 over 2.
Yep,
Yep.
like I said, I don't have the graph right in front of me, so I don't know the exact answers, right? But it would just be rise over run over which part of the function you're talking about.
Okay, and then cosine times pi r squared times cosine of 30.
Absolutely.
Okay.
Yeah, and the fact that we need a changing slope sort of supports the fact that Faraday's law says if there's no changing flux, then there's no EMF. For instance, for that middle part where it's flat, the slope is 0, but we also won't have a changing EMF. Oh, sorry, we don't have a changing flux, which means we don't have an EMF.
The second part of the question was, what is the direction of the induced current from 0 to 2 seconds?
Yep, that's a Lenz's law thing. So the B field is pointing out of the page, or the component of the B field that's perpendicular to the area is pointing out of the page. And for that particular time, from 0 to 2 seconds, the B field is getting stronger and stronger. So it's getting more out of the page. It's getting more out of the loop. And Lenz's law asserts that whatever induced things will come out of Faraday's law act in a direction to oppose whatever caused them. So the B field is getting out of the loop, then the induced current has to B field set up by that induced current points down into the or opposite B field that's getting stronger. And that can only happen if the current is clockwise, because if I apply my right hand rule, sorry, I might have cut out there. But I is clockwise because that points, that would set up a B field to oppose whatever caused it. I don't know if I cut out there or not. It said trying to reconnect.
you did.
Okay.
Does that make sense? If you want, I think the second part of this kind of makes more. I'm gonna turn my camera on really quick. But essentially what Costin was saying is that, Tyler, will you scroll a little bit back over to the picture? So it's asking you to find was the
Direction of the induced current.
That's okay. Thank you. So I could not remember for induced current, but what that does is opposes change in flux. And so what we're looking at here is that you have your B field pointing up and your area pointing up. So over time, if you're looking at that graph and stuff, you can see that it's increasing with the direction of your B field in your area, right? So your flux is getting bigger and bigger as time goes on, like upwards. And so in order to oppose that, your induced current would have to go downwards. And that's why you get clockwise for it.
Okay.
But like on the contrary, I know it's kind of weird to think about, but I think what kind of helps visualize is, let's say you have the same example, but let's say your area is getting smaller. So if your area is getting smaller and smaller, that vector that's going vertically is getting shorter and shorter, right? Because you have less flux going through. So your change in flux is actually down for that situation, which means your induced current would go up or counterclockwise.
Okay.
Does that make more sense, kind of?
Yes.
Cool.
Cool. Yeah, Lenz's law is definitely a little confusing, but I'm glad you asked that because that's a good problem. Cool.
When exactly is the final exam?
Should be Monday from 1 to 3 p.m.
Okay, 1 to 3 p.m. Monday. Okay. What?
And I believe once the final exam sign-up sheet has been finalized, then room assignments will be posted. All right, so probably sometime Saturday.
I'm pretty busy right now, so don't know about room assignments, more like Zoom links, but yeah.
Yeah, sorry, that's what I meant. Virtual room assignments.
Yeah.
Cool. So does that answer all your questions about block 3? Block 3 was a pretty
Yes.
pretty important block. I wouldn't be surprised.
Yes, thank you so much.
Cool. Yeah, not a problem. It's our pleasure.
Okay.
All right. Kaylin, you're the last one left as far as questions go. What would you like to see?
I don't have anything in particular.
Okay.
Yeah, I think I'm good.
You think you're good? Okay, cool. I was about to ask. I was like, we can go over whatever you want. You got 3 TAs to ask, so it's up to you if you got anything.
Yeah, I'm good. Thank you.
Cool, not a problem. Well, we appreciate you guys showing up. There's only, 3 or 4 people, but it's nice to have some support. So we appreciate it. Best of luck to you on the final. Please reach out to us if you have any questions. All right.
Okay, thank you guys.
Cool. Have a good
Yeah,
night.
no problem.
You too. Bye.
Bye.